Hi, my name is Sanjit.
And my name is Manvith, and today we'll be talking about the CMB and the observable universe, the entire structure of the universe.
This is in Unit 1, Formation of the Universe, in our astronomy course of Astronomy 101.
So let's get started. So, let's talk about the cosmic microwave background radiation first. We've all heard about the Big Bang theory, how the universe began. We have never proved it, but we have gotten close to the truth. This is important proof for the Big Bang is given by something in the backstage of the universe, the cosmic microwave background radiation. What is this though? When the universe was just around 380,000 years old, after the Big Bang, when the microwave background radiation took its first breath. But why is this so important? The cosmic microwave background radiation gives us evidence for the Big Bang as it allows us to see the furthest back in time. Right after the Big Bang, the extremely hot universe was opaque. Light wasn't able to penetrate it because of all the hydrogen gas and helium gas. But as the universe cooled and expanded, there are more remnants of background radiation, the cosmic microwave background radiation. This radiation describes the layout of the universe. The CMB looks different in different parts of the universe because some places are hotter and some are cooler, which actually corresponded to the slower expansion rates and also the faster expansion rates in the universe. Learning more about this property of the universe allows us to learn more about the early stages of the universe where light was first allowed to travel learn anywhere. Learning more about the CBR can tell us a lot about interstellar structures of the universe, like stars and galaxies. For instance, we can see the red shift and blue shift to discover more about how old a particular object is. Now, the CMB contains a lot more information about these structures, which we will introduce to you now. Also, the hotter and denser areas of the CMB, which are the red and yellowish parts you see in the picture, corresponds to the structure of the universe we know today, such as galaxies, superclusters, galaxy groups, and etc. And the reason for this is because the hotter and denser areas had were more dense, and so the gravity caused more gas and dust to accumulate, which made the fragments of the universe, which caused the first galaxies and superclusters, and the darker, the less dense areas, which are the blue areas, were the voids of the universe. Now, Sanji will be talking about the solar system of the universe.
I'm going to be talking about the solar system. The solar system is a system of planets orbiting a star, as you all may know already. Our solar system has 8 planets, maybe 9 if you want to consider Pluto, but yeah, it's not. And it's located in the Milky Way. We will be talking more about our solar system in the next unit, but the idea of a heliocentric solar system was first proposed by Copernicus in his book on the Revolution of Celestial Spheres in 1543. Next, we're going to be talking about galaxies. A galaxy is a system of stars, solar systems, interstellar gas and dust, and dark matter that is bound all together by gravity. Our solar system is in the Orion arm of the Milky Way galaxy, and our galaxy is part of another big structure called a galaxy group, called the local group. The Milky Way galaxy was discovered in 1610 by Galileo. The Milky Way is approximately 105,700 light years away in diameter, and the Orion arm is about 10,000 light years long, which is a minor arm of the Milky Way, and was also discovered by Galileo. It weighs up to 10 to the 12 solar masses, an astounding number. Next, we are going to talk about galaxy groups. A galaxy group holds hundreds of galaxies or fewer, and the Milky Way galaxy is in the local group alongside 50 other galaxies. The local group is on the outskirts of the Virgo cluster. The local group was discovered by Edwin Hubble in 1936 in his book The Realm of the Nebulae, and is 10 million light years in diameter. It weighs 10 to the 12 solar masses because of its vast size and the amount of objects it contains. Galaxy groups are formed when the clumps of dark matter and their associated galaxies are pulled together by gravity to form galaxy groups. Basically, these are gravitationally bound systems. So that's why you might see like the Milky Way and Andromeda moving closer together because they're in a galaxy group. Whereas if you look at other galaxies, they'll be moving farther apart because of dark energy. Next, we're going to be talking about galaxy clusters. A galaxy cluster contains hundreds, if not thousands, of galaxies. Galaxy clusters also contain super hot gas, tens of millions of degrees Celsius. The Virgo cluster is part of the Laniakea supercluster. The Virgo cluster was discovered by Charles Messier in 1781 and was the first galaxy cluster to be discovered. The Virgo cluster is about approximately 14 million light years in diameter, and it contains more than 2,000 galaxies. The mass of this supercluster is 10 to the 15 solar masses. Galaxy clusters are formed when clumps of dark matter and their respective galaxy groups are pulled together by gravity. Next, we're going to talk about superclusters. A galaxy supercluster is a collection of galaxy clusters, galaxy groups, and individual galaxies that are not gravitationally bound to each other. The Virgo cluster is in the Virgo supercluster and is 110 million light years in diameter, which is a lot, or 33 megaparsecs. It weighs 10 to the 15 solar masses, and it's, as you can see, it's really big. Galaxy superclusters are formed when clumps of dark matter and their respective galaxy clusters are pulled together by gravity. A galaxy. Next, we're going to be talking about galaxy megaclusters, which Manus is going to introduce.
So, a galaxy megacluster is a collection of superclusters. The Laniakea supercluster is technically a megacluster since it contains superclusters, clusters, groups, and galaxies. It is 165 megaparsecs in diameter. 1 megaparsec is equal to 3,262,000 light years. So it's really big. And 1 parsec is 3.262 light years. It is home to more than 100,000 galaxies. It weighs 10 to the power of 17 solar masses, 100 million billion times the sun's mass. The Laniakea supercluster is also the biggest supercluster in the universe. It was discovered in 2014. Galaxy megaclusters are formed when clumps of dark matter and their respective galaxy superclusters and clusters are pulled together by gravity. Now, Sanjay will be talking about the intergalactic medium.
The intergalactic medium is made of gas and plasma, which is a mix of atoms and electrons with an electric charge. It is found in the space between galaxies, and it can also get super hot, reaching millions of degrees Celsius. But the medium is also very thin, only 1,000 atoms per cubic foot, which is a billionth of a billionth the density of Earth's atmosphere. It's very hard to detect because even though it's very hot, it is really dim, extremely dim, because it's so spread out that it doesn't produce that much light to as when compared to galaxies and stars. The medium is made up of hydrogen and helium left after the Big Bang. There have been many more heavy elements in the medium, such as oxygen, since supernova explosions are spilling out those elements into the medium. IgM was created by supernovas that spewed helium and hydrogen into voids of space. Next up, we're going to be talking about the galaxy walls.
Galaxy walls, or galaxy filaments, are the largest structures in the universe to be gravitationally bound. They can stretch hundreds of millions of light years across, sometimes even billions, but they are relatively thin, about 20 million light years deep. The first galactic wall was the Coma Wall, also called the CFA2 Great Wall, in 1989 by Margaret Geller and John Hersha. It is 500 million light years across, 300 million light years wide, and 15 million light years thick. There is also a galactic wall behind the Milky Way, which we cannot see that well because of the zone of avoidance. This is a zone which is hard to see since the wall is behind the Milky Way and the Milky Way blocks our view of the wall. The biggest structure in the observable universe is the Hercules Corona Borealis Great Wall, which is a filament and is 3 gigaparsecs long or 10 billion light years long. Now we will be talking. Now we will be talking about filaments. Cosmic filaments are dense strands of galaxies and dark matter. They hold most of the universe mass and matter. Filaments are the threads connecting the cosmic web together. They also twist like corkscrews as they spin. They pull matter toward galaxy superclusters as each strand ends. The Laniakea supercluster is part of the Pisces Ceres supercluster complex, which is a filament and is 1 million light years long and 115 million light years wide. Filaments were created because the dark matter and sprinkling of normal matter clump together, forming filaments. We still don't know how filaments twist and generate torque because they are so big. And to be honest, they shouldn't even generate torque because they are huge, and it defies the laws of physics since they spin. Now I will be talking about the cosmic web. The cosmic web is where all the filaments connect to each other, creating the final structure of the observable universe, and is where all the galaxies, clusters, groups, superclusters, and walls, and it contains most of the matter in the universe. The cosmic web is formed as galaxies and other gravitationally bound massive objects come together due to the gravitational force. Where filaments intersect, there are superclusters and galactic walls. Dark matter created the cosmic web. The cosmic web was discovered by the James Webb Telescope by sending out gamma ray bursts. There are also voids between the filaments of the cosmic web called cosmic voids. In the voids, there is almost no matter, and there are very few galaxies, and there are almost all empty space. The voids in space are caused by varying densities in the CMB. Remember in the start how I told you the dark blue areas had very low density? Well, that's what caused the cosmic voids in the space. And the really hot and dense areas in the picture is what caused built the cosmic web. The biggest void in the universe is the Low's North 13788 void, which is 2,953,000,000 light years in diameter. So it's really, really big. Now, Sanjay will be talking about the observable universe.
The observable universe contains everything we see and is 93.016 billion light years in diameter. Even though the universe is only 13.8 billion years old, the universe expands faster than light because of dark energy, since it's not an object but space-time fabric itself. This means that even if you had to travel the speed of light from one theoretical end of the universe to another, you will never be able to reach the other side, since the rate of expansion from dark energy will never allow you to catch up to the other end. So, whatever, even if a photon travels at like the maximum speed of light, it will never be able to cross the distance of the whole observable universe.
Yep. And finally, we have reached the universe. The actual universe could be infinite, or our universe could be filled in a multiverse filled with infinite universes. We might never know the answer to this question. Thank you guys for all watching this video, and we hope you enjoyed it. And one little fact for you guys is that the cosmic address of Earth is Earth, the solar system, and then the Orion arm, then the Milky Way galaxy, then the local group, then the Virgo cluster, then Virgo supercluster, then the Laniakea supercluster, then the Pisces Ceres supercomplex, the cosmic web, the observable universe, and maybe then the multiverse. And so put down below what your cosmic address is. So in the YouTube comment section. So thank you for all watching this video.
See you in the next video.
Yeah.